In this video, we're going to talk about the idea of expected value. And the easiest way to think about expected value is it's like an average, but it's a weighted average. So we want to weight events that happen more frequently higher. So let me kind of explain what I mean. So imagine we have these two spinners, spinner A and spinner B. And the way the spinner works, of course, is you have this arrow in the middle and you give it a flick and the arrow will spin around and it will land in one of the two regions. So the first one is a region with a 1 and the second is a region with a 2, and same over here. Well, in spinner A, it's equally likely, pretend that this is an exact circle and this line is splitting the circle in half. But it's equally likely that I'll land in a 1 or a 2. In the second one, that's not the case. 2 takes up 3/4 of my circle, whereas the 1 takes up just a quarter. So the question is, what would be the average spin if I spun each spinner a large number of times? Okay. Well, remember, averages, you just add up all the numbers and you divide by the number of numbers that you are adding up. So it's going to be a similar idea. But in the first case, you could imagine, I think intuitively, you would imagine that the average value that you'd spin, you'd probably get a 1 and a 2 an equal number of times. So the average, if you spun it a whole lot, would be right in the middle. It would be 1.5. However, if 2 is a bigger region than 1, you would expect on average to have more 2s than 1s. In fact, 3/4 of your spins, roughly, would be a 2, and 1/4 of the spins would be a 1. So you expect spinner B to have a higher average. And the way we calculate this is we say, okay, 50% of the time, with a probability of 0.5 or a half, we get a 1 in the first case, and 50% of the time, we spin a 2. So for spinner A, the expected value, and we usually write it like this, E of x, so this means expected value, well, it's going to be half the time. I'll use my fraction. So this is the probability that I roll a 1. So half the time I roll a 1, and that is the value 1. And half the time I roll a 2. So it's the probability that I roll a 2, or spin a 2, times the value of 2. And this is, of course, a half times 1 is a half, and a half times 2 is 1. So on average, I would expect my average spin to be 1.5. For spinner B, it's going to be the same type of idea, except my probabilities change. So for spinner B, our expected value, or weighted average, well, this time, 1 is only 1/4 of our circle. So the probability that I flick the spinner and land in a 1 is 1/4. So that is the probability of spinning a 1 times the value 1, plus, well, we have 3/4 left of our circle, and that's all 2. So 3/4 of the time, that's the probability that I get a 2. I get a 2. So it's a probability of 1 times 1 plus the probability of 2 times 2. So 1/4 of 1 is 1/4. And maybe I'll write it like this actually as 0.25. I'll do it in decimals. 3/4 times 2 is 6/4, which is 1.5, 1.5. And this is 1.75. So on average, my spin in the second spinner is going to be 1.75. If I spun this a large number of times and took the average would get really, really close to 1.75 and would get even closer the more times I spin. And a couple of notes, and I think these are going to be kind of obvious, but I'll just say it verbally. But just looking at this, both of these spinners, and in fact any spinner that just has a 1 or a 2, I can't have an average that's lower than the smallest number or higher than the largest number. That's impossible. So all of my averages, no matter how the spinner looks, as long as there's just a 1 and a 2 section, I know that my average spin, my expected value, is going to be between 1 and 2. And in general, let's write this in general here. Now let's give myself a little more room. So I will scroll up here. In general, for an experiment, with outcomes, let's call the outcomes x1, x2, x3, x4, all the way to xn. So let's say there's n outcomes. Then the expected value, the average, is going to be the probability that that outcome happens times the value of that outcome. And we do that for each outcome. So the probability the outcome happens times the value all the way to the final one, the nth one. So for each outcome, we multiply the value of that outcome times the probability that it happens. And just to make sure we know what this applies to, the outcomes need to be numerical. If we have something with just categories, like maybe favorite color or something, then we can't multiply something like if the probability of liking a half was, or liking blue was a half, we can't multiply a half times blue. That doesn't make any sense. So expected values only work when the outcomes have numerical values attached to them. And let's do a couple of examples to make sure we know how this works. So let's look at this game. It's a lottery. So the idea is there are 12 numbers, say 1 through 12. And there's nothing special about the order of them. You can think of them as 12 symbols. And just like a lottery, you choose some of them on a ticket. So we're going to choose 3. And then they draw 3 of those numbers at random. So the prizes work as follows. If 2 of your 3 numbers are drawn, you win $50. If they draw all 3 of your numbers, well, you're in luck. You win $500. And otherwise, you lose $10. So it's $10 to play. So what is the average amount you win or lose per play? So that's what we want to work out. So This one is a little involved in terms of working out the probabilities, but we'll get to that in a second. We can set everything up in a little table to help us out. So we need the following things. So we have our values, we'll call them the xi's, the probability that those values happen, so the probability that xi happens, and to help us calculate, let's multiply those together. Probability of xi times xi. So our values for this experiment, well, there's 3 of them. We can either win $50, so that's one value. Our first value is winning $50. Our second value is winning $500. And the third value is losing $10. So that's a negative 10. So we have a little bit of work to do to figure out the probability of each of these numerical outcomes happening. So pause the video now. Think about this problem. So this is very similar to some other probability problems that we did involving picking people for a field trip. So maybe you want to go back to that video and think about how these problems relate. If you can think about how those problems relate, then you should be able to fill in these probabilities here. So pause the video and think about trying to calculate these 3 probabilities. Okay, so now that we're back, let's scroll down here to give myself a little more room, and let's see if we can figure these out. So remember, winning $50 was here's your 3 numbers that you picked, and here are the other 9 numbers that you didn't pick. So let's think about how these would get picked in a lottery. So in this case, the $50 case, this is 50. So 2 of your 3 numbers are chosen, and 1 of the other 9 are chosen. So they're picking 2 of your 3 are chosen, and say 1 of the other 9. And if you think about it, what numbers get picked out of your 3 don't affect the choices out of the 1 of the other 9. So those choices are independent. So it's 2 of 3 picked and 1 of 9. And remember, when we're picking, you can use, there's 3 things in total, so there are 3 total. There's 2 that are picked and 1 that is not. So this is an arrangement problem with 3 symbols, 2 checks, and 1 X. And for the 9 total, there is 1 check and the other 8 X's. 8 X's. And that will give you any arrangement of the 2 checks and the 1 X will give you a different combination of your numbers that are chosen. And any arrangement of the 1 check and the 8 X's will give you a new way of picking 1 out of 9. Now, I'm going a little overboard in this case. I just did this kind of the long way because you can use this method for more complicated problems. But how many ways are there of picking one thing of 9? Of course, there's 9. So I know that this bit here, there's 9 different ways. And you could even see this. This is going to be 9 factorial divided by 8 factorial, which will simplify to 9. But you can kind of logically see very easily there are 9 ways of picking one of these numbers that you didn't pick. And 2 of 3, again, it's pretty easy. You could figure it out. It's 3 factorial divided by 2 factorial is 3. Well, there's only one number that doesn't get picked. So, depending on where that is, there are 3 different choices. So, in total, the number of ways that you can get 2 picked out of your 3 and 1 picked out of the 9 that you didn't choose, that is 27. So 27, where 2 of the numbers are yours and 1 is not. And how many total ways can you pick 3 numbers out of 12? We should actually do that so we can work at a probability. So the total, I'll do it up here. So there's 12 numbers, 3 picked, and 9 not picked. So this is going to be 12 factorial over 3 factorial times 9 factorial. I'll leave this as a little exercise. So that's going to be 220. So there is my denominator. That's the total amount. So the probability of getting 50 is, of course, the number of successes over the number of total ways of picking. And there are 27 successes over 220 in total. So our probability here is 27 over 220, which is just over 10%. So we figured that out. I'll leave the last row until the end, so we can just multiply, and it'll be quite easy. So let's do the next one. Let's do the probability of getting 500. So remember, let me scroll down a little bit. So 500, you win $500 when it's 3 of your 3 numbers and none of their 9. And how many ways are there of getting your 3 numbers picked? Well, of course, there are 220 different ways of picking 3 numbers out of 12, and only one of them is your 3 number. So this one's really easy. This is just one. There's one way of picking all 3 numbers of the 3 that you picked, and there's one way of choosing none of the 9 numbers, and that's by doing nothing. So, of course, there's only one way. So the probability of getting $500, remember that's them picking all 3 of your numbers, is 1 out of 220. So we can go up here and put that in to our diagram. Let me scroll up here. It's not going to do it. There we go. So the probability that I win $500 is 1 out of 220. And the probability of losing $10, well, you could figure it out in the way of getting 1 of 3 of your numbers and 2 of 9, or 0 of 3 of your numbers and 3 of 9 of the others. Or you can use the idea that the exhaustive outcomes here, the probabilities, have to add up to 1. So we're going to do that. So it's going to be 1 minus, we already have 1 out of 220, and we already have 27 out of 220. So the rest of the probability must be this minus 10 result here. So this is 220 over 220, so we have, that's 28. So what we have left is 192 over 220. Okay, let me kind of box those in to make sure we know what they are. There we go. And now to help us, this is getting a little messy, I apologize. We're going to have to use this spot here. So I'm going to make a little extra box. So now this entry here is just going to be multiplying along my columns, multiplying the probability by the outcome, by the value of the outcome, I should say. So this is 27 over 220 times 50, and you can check that this is 540 over 220. Here we have 500 times 1 over 220, which is 500 over 220. And here we have 192 over 220 times 10, so this is negative 1,920 over 220. Okay? So we worked out the probability of each outcome times the numerical value of each outcome. So to figure out the expected value, let me erase this just to make a little more room. I'm just going to add along that last row here. So the expected value is going to be, well, 540 plus 500. Notice they're all over the same denominator. Plus negative 920. And that equals negative 880 over 220, which is, you can see kind of immediately that simplifies to negative 4. Well, what does this mean? Okay. So what this means, I'll finish it off here. I'm going to erase a little bit. Remember, this is a video, so you can always rewind if you want to see the calculations otherwise. So I'm going to erase this just to make a little bit of room to help me write down my final sentence. So, on average, if you played this game a whole whack of times, you would lose, since it's negative, $4 per play. And remember, that might not happen the first, 10 times you play. Your average, maybe you were really lucky. Maybe you got a 500 or something, so your average would be quite high. But if you played this, say, 10,000 or 100,000 times, well, the law of large numbers would start to take over nearly for sure then. And your expected value, the average outcome that you would get if you kept track of all your outcomes, add them together, and then divide by the number of games you've played, you would get something very close to negative 4. So that's how expected value works. The key is figuring out the value of each outcome, figuring out the probability that that outcome occurs. Sometimes it can be a little bit complicated. In this case, it was. It had to do a little bit of counting. And then multiply the value by the probability, then add them all together for each column here, and that gives you your expected value.